Hello everyone, good morning and welcome to this webinar. I'm Pelagie and I'm in charge of the communication and dissemination activity on the EUPEX project. I've taken over Pascal's activities since she's retired and I'm now organizing a webinar. So today's webinar will be on Ocean, an admin software cluster stack used by the CEA and also used in the EUPEX project. Okay. But before diving into today's topic, I just want you to know that this webinar is part of the series. Under the EUPEX project, we are organizing monthly webinar to share the application and the tools used within the project. All these webinars are recorded and you can find them on our website or on our YouTube channel. This webinar is our last before the summer break, but we will come back in September with new webinars. Now let's move on to today's webinar. It's called A Practical Approach to Ocean, an admin software cluster stack used by the CEA. Ocean is a software stack providing tools and documentation for heterogeneous cluster management. In this webinar, you will learn how you can use Ocean on a daily basis to deploy and administrate HPC cluster. Our speaker will be Aurélien Séden from the CEA. Thank you so much, Aurélien, for participating to this webinar. We are so pleased that you accept our invitation. So Aurélien is a senior researcher at the CEA. He is in charge of HPC storage strategy and system administration. He is also chairing at the LAD, a dedicated conference organized by the CEA, and he is leading the development of Ocean. Now the floor is yours, Aurélien. I will stop sharing my screen.
Okay, so thank you, Pelagie, for this great introduction. Let's share the screen now. Yeah, here. Let's go. Yes. Okay, so hello everyone. I hope you can see my screen and everything is working.
Yes.
Right, perfect. So I don't have to introduce myself. It's already done, so perfect for that. I will start this presentation about Ocean at CEA, so our administration distribution. So the agenda for this talk, we will start with the origin of the project to give you some context about Ocean and where it comes from. Next, Ocean is in two parts. We have two parts in this project. We have what we call Ocean Stack and Ocean Core. I will explain what is it just after that, but I will go deeper in these two topics on this talk. And next, I will give you a use case of what we need to do when we want to update a software inside Ocean. And the example we have today will be Slurm, which is an interesting software because it has a lot of dependencies. And during this use case, you will, if you want, you can ask me a question and ask everything you want about how to do and how to deal with this kind of update inside Ocean. So the origin of the project. So at CEA, we have a lot of different stories with clusters, and let's get started with the Terra 100 project. which introduce a centralized cluster file system. Before that, we have the Terra 10 project, which is a cluster with the storage administrated inside the same cluster. So we shared the computation stuff and the storage stuff on the same teams, and the cluster has its own cluster file system, which was managed by Atos, Bull, and now Eviden, which is quite complicated to choose a name for this, but yes. That was my first cluster, and how we manage that. So everyone managed cluster and the cluster and the compute machines. Next, we have another project coming after that, which is Terra 100, which introduced a central cluster file system, still managed by the same team, so Atos and Bull at this time. And what it changes is that instead of having just one team managing the computation stuff and the storage stuff started to get a part of the computation part. So with that, the CEA start to think about its own cluster stack, because when you share this different component, you need compatibilities, and it's quite hard to have this compatibility with potentially different providers. So we started to think about that at this time at the Terra 100 project. Next, we have the Terra 1000 project, which is the evolution of the Terra 100 project, and we started to have the storage the availability to have storage appliance with new hardware provided by DDN. And with that, we have the availability to have our own VM on this appliance. And by this technical choice, we started the Ocean Core project, which provides the complete cluster software stack from CEA. So this is where we come from the Ocean project. At this time, there is no Ocean Core. It was called Ocean only, but to give you the corresponding names now, it's Ocean Core. And in parallel of this project, we have the R&D cluster, and on this cluster we have a lot of stuff to manage with next-gen hardware, with exotic interconnects, and so on. And we have a lot of different hardware to manage, and it's really difficult to manage with one provider. And to have something smooth and to have the same softwares, we need to concentrate every piece of this software on something common and easy to manage. And so to manage this cluster, we use also Ocean, which is a distribution, and which will provide all the different software we need. So we extended the Ocean Core coming from the storage part to the administration and the computation part. Of course, with that, we have a lot of feedback for the past and current experiences with our clusters. So to give another context, so what we have and what we need to manage here at CEA. So we have the project EXA now, which was Terra before, when we have 3 compute clusters, about 20,000 nodes. We have a storage cluster to manage. So like I said, the storage part is apart from the computation stuff. And it's centralized with a different team, and everything need to work together. And we also have what we call after at this time big data cluster, which is a stat cluster, statistics cluster, where we store data from the different counters and so on from the cluster and the compute cluster and the storage. And we have these three different clusters to manage, and we need to have the same software and the same a centralized point to manage every software from these three different parts. So we have EXA, we have also the TGCC and the CCRT center, and it has also different clusters, so 2 compute clusters and a different storage cluster. So we are about 10,000 now nodes on the compute cluster, with a dedicated storage cluster, and also stats clusters with the L key and so on. And we have the R&D cluster with heterogeneous hardware inside and a dedicated storage also. So we have many different softwares because we have different stacks, and we need to, and we before Ocean, we wasted a lot of time to replicate the administration technique and to maintain the different softwares at the same level on the different part of these three parts. So the Terra, TGCC, and R&D cluster. So that's why we created Ocean, and we make this evolution from the storage part to the computation part and the administration part. So we come up with 2 parts in Ocean: the Ocean Core, which is only the packages, and Ocean Stack, which is the way to share the different administration project and administration component. It allows us to have the same method to install stuff and to maintain the different component. And with that, we also have a way to support heterogeneous hardware with different software stack on the same with the same process. So what you can see here on this picture, you have Ocean Core that we can imagine that it's a lot of different bricks, Lego bricks. Here, this is this picture, where we have the software for the storage tags, for the admin tools, and sometimes patched software, because HPC is something that could lead to make evolution on the existing softwares. So that's why we have also patched software here. We have Ocean Stack, which is a blueprint and documentation about how to use these different bricks, Lego bricks, and you have this. This is a plan of how to build a cluster and have these different bricks come together, which will lead to an HPC cluster with shared practices, shared admin tools, and where we can have different hosts and vendors talking together, let's say. So I will start with the Ocean Stack. And this is a basic schema of what is the central idea of Ocean Stack. So Ocean Stack, the basic idea is to have one administration islet. In this talk, I will talk about islet or island, which is let's say interconnected island, but this one is the central one, which will install the other one. So on this administration islet, we will install different servers with Ocean. So it's a centralized management point to provide the different OSs and services for the different other part. So what you can see here, you have the administration islet, and you have compute islet around, and the storage islet also, and the login islet also. So what it says is that if you need, if you want to add another computation island with different hardware, different vendors, you can add another one and plug it on the administration islet. And this administration islet will provide also monitoring and base services to monitor everything on this different islet and on this let's say computation center with the storage and so on. So Ocean Stack will use this administration islet, sorry, will use Ocean Core and follow the Ocean Stack guideline to install the administration islet. So with this solution, we currently manage 20 to 10K nodes with Ocean because as you know, the clusters can evolve, and we went up to 20K nodes, and now because we some nodes was not so performant, so we left them, and with this evolution, we are now more with 10K nodes. So that's why you have I say that, and with Ocean, we can manage multiple OS with different kind of OS. This is thanks to the administration islet and the different services we can provide with that. And with this, we can also provide an evolutive administration platform, because we can add some new servers inside this administration islet to increase the performances if needed, and so on. Going a little deeper inside this architecture, here you have a more detailed schema of the administration islet here. So the upper part, and in this central picture here, in the center of the picture here, you have the switches. And here, if you see the islet 10 and islet 20 here, this is two different islets. And in the upper part is the administration islet. So on these servers, what's the goal of this administration islet? The goal of that is to provide the reference of the cabling, the hardware cabling of the different hardware we have. So we do that inside DB and tools that we make, and this is in-house tools, and we can describe all the let's say the hardware and the location of the different hardware inside the room and inside the racks. So it allows us to see the different movements, the different hardware movements. So when we change a component, we can redescribe it inside. So that's what provides this islet, administration islet. It does, in fact. I use a future, but it's not future. It use right now as this kind of stuff. So the goal is also to provide IP address management, so what we call IPAM. So to address every node on the cluster and so on. We have core services like DNS, DHCP, HTTP. We have also diskless image management. We have also diskful deployment services, and all that is done by with in-house developed services. And the goal of this is to host anything that is required for the fabric manager, the different vendor tools, and the resource manager and external services. So the idea is to have these services. Once you have these services on the different islets, we will have some caches of these services providing a scalability. In OceanStack, I will just present you what we are using inside the administration islet. In this administration islet, we have a storage to manage the different configuration. And for that, we are currently using ClusterFS, which is let's say a file system that can evolve easily with triplet of nodes to have a quorum. So the minimum configuration we need to have the administration islet is to have 3 nodes with some disks inside to create volumes. Inside these volumes, we have one volume dedicated for diskless images and software repositories and VMs. So it's sharded with one replica. And we have 2 replica for admin storage, which is a Git repository. We use Git to store the configuration. In fact, we are using Puppet for all the configuration of all nodes and to manage the story and the evolution of the different configuration. We use a Git repository, which is stored inside this ClusterFS, and all the different configuration files, like the switch configuration. That's something I didn't mention before, but we can also configure all the switches inside all the islets and on the admin clusters. For VM management, we have a Peacock tool. So it should be a well-known tools at CEA because we are using that for users, but in Ocean we are using that also for to create the different VMs and the different services. The idea is for each services we have a dedicated VM. For example, I talked just before of HTTP services. To host the HTTP service, we have a VMs for that, and we are using Peacock to manage this different VM. Peacock orchestrates the VMs and the network setup tasks. Another point I should add here is that Peacock also manages the location inside the host, and it can pin the VM on processes and on hardware, which is really important to have when you need some performances on some services. To manage the high availability, we are using a tool which is Fleet. Fleet was maintained when we started the project, and we choose to fork it and to use it on our system. It's a CoreOS tools, and globally the Fleet tools combine the systemd and etcd to build a distributed systemd framework, and with that we can manage and see all the services and all the different VMs running on our system. For load balancing, for load balancing, we are using HA proxy, which allow us to to have an entry point for different services, for HTTP, for example, for the Puppet configuration also. So we have different load balancing. LB means load balancing here, instances sharing virtual IPs, and we have for LDAP and HTTP an entry point on this load balancer services, redirecting to different VMs hosting the LDAP or the HTTP services here. For the virtual IP management, we are using KeepAlive, KeepAlive-D, which manage the IP and is aware about if the IP is up or not, and choose to switch the IP from one node to another one, which is really convenient with these models, because what we want to have is to have at least two services for two machines for one services. For HTTP, for example, we have two VMs with two HTTP servers with one IP distributed on each server, and it allows us to make smooth updates without any interruption on the administration cluster. To manage the infrastructure modeling and IPAM, we have in-house components which is Confiture. Confiture is one of our project, which is all these tools are available publicly available on CEA HPC on GitHub, and it's based on rec tables, which is a database and a web interface that shows the different components and location of the different components, and also the cabling details and descriptions. With that, we can generate configuration files for DNS, DHCP, Conman, and switches also. For switches, it depends of the model, of course, and we have some templating for that. For boot management, we have also an in-house component which is called BMGR. BMGR is manage the EUPEX, Kickstart, and Cloudinix stuff. The idea is when a node boots, it will just have to know which configuration it needs, and it use the BMGR service to describe this its need, in fact. So after this list of different tools we are using inside Ocean Stack, let's talk about the different design and how we want to use that, and what is the idea, the global idea behind that. So the idea of Ocean Stack is to have a pragmatic solution in mind, and to use it to use what we are using in production. In fact, these tools are open source or in-house. When it's in-house, we tried, and I think we achieved to provide that in an open source forms on the HPC CHPC stuff in GitHub. So all you have here is available on GitHub, all open source, and try to keep it as simple as possible. So it's not really KISS, but we try to get closer to the KISS principle. So for Ocean Stack, we have concrete stuff there behind the Ocean Stack is some documentation with blueprints, with the design and guidelines that are applied on each cluster, and how to install the different components I described just before. So we can modify that if the requirement evolves, or if we need to adapt some different services for the clusters to provide more and more performances on these services. So we have documentation, administration guides, and operational procedures, depending on the service, of course. And the idea is how to integrate, to describe how to integrate the different islands or islets, and how to operate the cluster. Okay, so now we have the picture of how Ocean Stack is, what is Ocean Stack and what it needs. And it needs, of course, Ocean Core. And this is, Ocean Core is a distribution. So it's the RPMs, because we are based on RPMs, needed to install the different components. So right now, Ocean is based on a Linux distribution, based on we have two branches and two versions, the 3.x and the 3, now it's a 3.8, which is based on Alma Linux 8.8. And we will soon release the 4.4 based on Alma Linux 9.4. So as you can see on the picture on the right, is that we have a Linux distribution here. We have the updates of this Linux distribution. We have EPEL, so it's not, of course, this Linux distribution is based on the RPMs and is compatible with EPL. And on top of that, we have Ocean. It's a global picture of that. Of course, we can add some extra repository. It's not shown on this, but on this schema, but we can we add some of them. Typically, we have external repository to manage the MOFED and for InfiniBand driver. Now it's hosted by NVIDIA, but we have this external repository. We also have some repositories for Puppet and so on. And all these different repository, all these different stack of repository, we build Ocean. And once we generate all the RPM based on this stack of repository, we have, as a result, an Ocean release. Once a version of Ocean is released, we have another repository called Ocean Updates, which will provide the dedicated updates in this repository. The content of Ocean Core is now we are about 154 packages, and inside that we have the different tools we talked before with Ocean Stack tools. We have the CEA softwares. We have some packages that we need to update. We need to update because the version was not so up to date, and we need the latest versions. We have also patched version, so some that are not publicated, and we need to add some custom patch inside, and some missing dependencies for different tools, for various tools, if needed. The key packages we provide inside Ocean Core is Slurm, so the resource manager that allows us to manage the different highlights and the different clusters. We have the raster file system, so it provides, of course, the parallel file system. We have also Puppet with a different configuration management. We have our own version of OpenSSH because we need to use a specific configuration for the login nodes. We also have a QEMU to manage manage the different virtual machine. So yeah, it's as you can see, we can have some key packages that can modify the distribution, the existing distribution. For I think about QEMU here and OpenSSH, but it's needed for us, and it fixes some bugs we need to do for that. So let's talk about how we build the package here. For Ocean Core, we have a tool that is called Rift. And Rift is a tool that will validate and build the different packages. It's based on the mock, which is a tool that can provide you a complete, not a complete, it's not a good word, but the simpler version of distribution of the core distribution with no dependencies, and it allow to build the different RPMs and not forget a dependency inside the spec file of the RPM description. Inside that, we are using RPM build, which is a common tool to build RPM, and we are using QEMU to launch a VM and to validate the package we built just before that. The different supported architecture are x86 and ARC64, and the programming language is Python, and it allows to publish and sign packages. So with Rift, you can create your own repository, and indeed we use that for Ocean, and the result of Rift build commands is a final repository, which is the one we publish and we are using, in fact, in production. To manage the different version of the packages, we are using Git. We have a Git repository which is hosted in the Gerrit tools inside internally. In fact, you cannot have access right now, for now, in fact. And this tool allows us to discuss and review the changes on the packages. And once a packager is fine with his modification, he submits these changes, his changes, and we discuss the different way to do the best we want. And once it's approved, it's directly published in the Ocean release. And this Gerrit is linked to a CI/CD process, which is Jenkins. So Jenkins will track the different changes from Gerrit and will launch the different tests. So basically what he will do is just to get the Git repository, get the last changes the packager proposes, and will launch Rift and the validation of the package. If the package is validated, it will advertise the Gerrit stuff and say that yes, it's okay, you can learn that or not. So the test is passed or not, and if it's passed, we can validate the packages. In Jenkins, we also do different tests, and the validation of all the distribution when a new package is available. So like I said, we publish package once it's validated, and we test that on our R&D cluster. So internally, it's our R&D cluster that will be used to launch the different tests. So Now I am on the final, on my final slide. I take an example of what a user wants to do when you want to update Slurm, or a developer. So Slurm is a batch scheduler that needs to synchronize version on client and server side. So when we are referring to the Slurm blueprint inside OceanStack, we have two servers communicating with compute nodes. So what are the steps we need to follow to update the new version of Slurm in Ocean? So first, the developer or the packager will need to provide a new package with an update of Slurm given a targeted Ocean Core version. So he will update the version, submit the patch into Gerrit, and wait for validation. Optionally, if there is some dependencies that are needed, he have to rebuild the dependencies also. Once every tests are passed and discussion with the release manager are done, and everything is okay, we push this version inside the Ocean repositories. Next, so it pushes it not inside the release one, but in a test one. Once it's tested, the version of Slurm is updated inside our R&D cluster, let's say, and we validate the new behavior. If some bugs are found, we add patches and we go back in the first step and going on the validation process and so on. And that's it. Once everything is validated on other clusters, we will publish that on the official version of Ocean, and it will be provided on the different version, on targeted version. So because we share the same packages on all the clusters, everything can be done smoothly on every cluster of the CEA with this method. So here are the website of Ocean with so it's ocean.opex.eu. You have inside the Ocean Core packages and the Ocean Stack documentation. We provide inside that a container with Rift installed inside the container that provides you a way to test the build process of Ocean. So you are not connected yet. You are not connected to the Git repository and the Gerrit and Jenkins stuff, but you can see if Rift how Rift is working, and you can also do your own repository if you want, but it's a start. And we have an ongoing work to migrate the CI/CD platform with Gerrit and Jenkins to an open forge, which will be a self-hosted GitLab here at CEA and publicly available. The idea is to ease the integration of new software and library inside the EUPEX project. And what we did also is that right now, Rift is open source and is provided on the HPC page on GitHub. So I think I'm done. If you have question or anything you want to know about Ocean, please go.
Thank you so much, Aurélien, for your participation to this webinar. It was really interesting to understand how Ocean works and how it could be used to deploy heterogeneous cluster with practical examples. So thank you so much.
You're welcome.
It's time for the Q&A, so please don't be shy and ask your question to our expert.
Yeah,
This
I've got a
is
question concerning the
sorry. Go on.
Sorry, concerning the PCOCC.
Yep.
Is there some advantage over PCS coordinating?
Over what? Sorry, I didn't. I didn't
Over
get
PCS
the.
and coordinating.
Oh yeah. In fact, it's quite different. We didn't.
Let me chat it.
Yeah. We didn't use. In fact, we are using coRoSync, but only for the storage part inside other VMs, right? We don't use coRoSync for all the administration clusters because it's quite hard to have a synthetic or a centralized information. It's because you have a lot of services and you need to describe very lot of things, and it was not convenient for us. And what we the idea behind because we use that before for Terra 1000 we use that and 100 also, and with the clusters coming bigger and bigger, we have a lot of services, and we used that before. So we have the PCS and all the services described inside. But once you need to manage more than 10K nodes, it's really painful to know what's happening inside this. So we try to simplify that and do one services by on one VM. That's the idea, or one or two, but like a coherent service inside one VM, and we just manage these VMs and manages that by test. We can test if a VM is okay inside the system like a systemd like service. So if the service is not okay, it will be just turned off and maybe restarted on other nodes. Yeah, that's why we didn't choose that. But we are using that on some services, not on the administration cluster. Did it respond to your question?
Yeah, Peter says thank you, so I think it's okay.
Okay.
Fabrizio, do you have a question?
Yeah. Did you try to install the OceanStack somewhere else beyond CEA up to now, I mean?
I try to sell that and to have some clients, but I don't have any feedback yet. I think the question is the Ocean ready for other platforms than our platforms, right?
Basically, yes. I mean, is it a product or it is a sort of in-house development?
No, the idea is that we can install that outside the CA. It's not. I mean, inside Ocean and OceanStack and so on, we don't have a hard requirement on our platform on our site. The idea is if you want to install the cluster and to install to fetch the different or to install a new cluster, the idea is that you can do that outside the CA. Because we have, in fact, we have different constraints. As you can see at the start of the presentation, we have the TGCC, which is a completely different environment than the Terra one. the Terra environment is really different. And because of that, we need to have an installation that can be done on the both sides and with different environment. So as far as I know, because I can tell that maybe we missed something, but the idea is we need to have something deployed that can be deployed everywhere. It's not CEA stuff. We try to get the common administration habit and try to get that on our clusters and on our installation.
Thanks a lot. My second question is, I've seen that you support x86 and ARP, basically. Do you have any plan to support also RISC-V?
Good question. In fact, I heard that RISC-V is something that is coming, but there's no plan yet to do that. It's not on our agenda yet. So maybe it's something we can schedule for the next Rift version, because it's Rift that will provide that, I think. But it's not yet on our timeline yet.
Okay.
And in fact, I can add something because it's coming to my head now. The hard part to manage RISC-V is to manage the tests. The compilation can be do easily because you have cross compilation and so on. But to test a RISC-V machine, it's not so easy. Because you need a VM and you need all the dependencies. Yes, it's something completely unknown for now, and yeah, we need to think about that if we really need it. Yeah.
Thanks a lot.
You're welcome.
Okay. Does anyone have a question? Another question for Aurélien? I think we are good.
Thank you.
Bye, everybody.
Yeah, thank you so much for attending this webinar. See you in September with our next webinar, which will be by Andrew Beggs on ECMW from ECMWF, and yeah.
Bye.
Bye.
Thank you.
Thank
Have
you.
a good day. Bye-bye.
Thank you.
Thank you. Bye-bye.